design example 4.8 from the course text. The objective is to design a source follower or a common drain amplifier configuration with the PMOS, with the P-channel enhancement mode MOSFET, to meet a set of specifications. Okay, so the specifications are: the circuit to be designed has a configuration shown in figure 28. You can see this over here. This is a PMOS MOSFET with drain. You can see the drain is connected to the ground, so the drain is a common signal ground. The drain is a common signal ground. Okay, the output is being taken from the source. Okay, so this configuration is a source follower configuration, which implies that whatever is the input is available at the gate, the output is going to follow that. The output is going to follow that, and the output will be in the same phase as the input at the gate. But with the voltage gain will be slightly less than unity as happens in source follower configurations. Okay, this is a source follower configuration, and circuit parameters are: you're given the VDD voltage as 20 volts. Okay, so VDD is 20 volts. Then the output source resistance, which is driving the circuit. This is your driver circuitry. Okay, VI is the AC signal, and RSI is 4 kilo ohms. Okay, the Q point values are to be in the center of the load line, with IDQ given as 2.5 milliamps. You notice that you don't have any VSDQ, but then since the specifications are as such that the Q point is in the center of the load line, it's good enough. Okay, the load line will look like something like this. You will have the drain current or the source current, okay, ID, and then you have this VSD over here on this axis. And if you recall, if you apply the KVL at the output loop over here, it defines the equation of the load line as VDD minus IS, or IS or ID is the same because the same current from the source that is going to flow into the drain. So I can write this as IDQ into RS, into RS, and this should be equal to my VSDQ. Okay, this is equal to VSDQ. So the thing is, when this VSDQ becomes equal to, when VSDQ becomes equal to VDD, then that means your IDQ is 0. Okay, when VSDQ is equal to VDD, if you look at this equation, then that implies IDQ is 0, and that is the point VDD on the VSD axis. Okay, where the current is 0, where the current drain current is 0, or the source current is 0. Then I need another point to draw a line on IV IV axis, and at this point you see VSD is 0. Okay, so where VSD is 0 is VDD over RS. Okay, the current is, you can put this IDQ as VDD over RS. So at that point VSDQ is 0. So this is VDD by RS. Okay, so if you're going to connect these 2 points, you will have a load line. We call this the load line. So let's connect these points. Okay, so somewhere in the center is a Q point. So these are the specifications of the PMOS amplifier configured as a source follower or a common drain circuit configuration. Okay. All right. So now we are given that IDQ is 2.5 milliamps. So let's write this down as over here IDQ. Let's remember this, that the Q-cent current is 2.5 milliamps. This is milliamps scale. Then since the Q point is supposed to be at the center of the load line, that means this would be VDD. Since this is from 0 to VDD, so this will be VDD by 2. So VDSQ is half of VDD. Okay, this is VSDQ. So this is a very important information. You see, as a consequence of this information, you can find out what the source resistance is. Okay, if you consider this equation, you see, you know everything except RS. Now VDD is known. Okay, you see VDD is given as 20 volts. You know what is IDQ is 2.5 milliamps. You know what is VSDQ for the center Q point biasing of the transistor. That is VDD by 2. So the only unknown is RS. I mean, I can write this down as equation as VDD, or let's put some values. So let's write this as 20. Now I'm putting the values in this equation. Okay, I'm considering this equation now. VDD minus 2.5 milliamps multiplied by RS. Okay, I don't know what RS is, and this is equal to VSDQ, which is what? Which is VDD by 2. So this is 10. Okay, so 20 minus 10 over 2.5 implies that my RS is 4 kilo ohms. Okay, so I have found RS as 4 kilo ohms as the source resistance, which would indeed produce the Q point in the center of the load line, so that IDQ is 2.5 milliamps, and it produces VSDQ of half VDD. Okay, so so this resistance is responsible for that. RS is 4 kilo ohms. Right. The other thing for to motive to evaluate RS was we are given the voltage gain in the specification that you look at over here. So what the question was saying was that specification, the input resistance was given as, so this resistance Ri, if you recall from the previous small signal model, Ri is basically this is the input resistance of the amplifier, which is in terms of the biasing resistances R1 and R2. Okay, since we are going to ground this, okay, this will be grounded. So the only common node is the gate node, and this R1 is going to come parallel with the R2. So your input resistance is nothing but R1 parallel R2. Okay, but in the question you don't know what, and this question you don't know what R1 and R2 are. Okay, you can find RS from the information that the Q point is at the center, and you know the drain current, so you know VSD. So from that, and from the output, considering the output KVL, applying Kirchhoff voltage law at the output loop, you can find what RS is, but you don't know what R1 and R2 is. Apart from that, the only information that is available is that the input resistance R1 R2 is equal to, since the gate current is 0, we consider the we're also neglecting any gate capacitances which are infinitely high, so we're not considering any gate reactance, capacitive reactance, but we assume that the input impedance or the resistance of MOSFET is very high. So this is only set by the input resistance for now is only R1 parallel R2. Okay, so this is my Ri, and that's also given. This is my Ri, R1 combination, parallel combination with R2. So that is 200 kilos. So that's 200 kilos. 200 kilo ohms. Okay, but we need to find R1 and R2. So the transistor channel width to length ratio is to be designed such that small signal voltage gain is 0.9, right? So we are given a voltage gain, small signal voltage gain, and if you recall the voltage gain relationship that we derived in terms of the output voltage by input voltage, this is my VI, input voltage, this is my output voltage. The relationship is given in terms of the source resistances, the output small signal resistance R0 of the transistor, okay, and then in terms of what is the source resistance and the input resistance of the amplifier. So we derived this relation last time in part 43 of this lecture series. Since this is known, so we are required to find what is RS, okay, so that the only unknown that is left is a transconductance gain, okay. So we can find this transconductance gain from this relationship. What about R0? You see R0, you don't need to consider R0 because I can see that lambda channel width modulation parameter is 0. Okay, so R0, if you recall from a previous discussion, is the output resistance of the transistor given in terms of 1 by lambda IDQ, right? Now lambda is 0 implies for the quiescent current of 2.5 milliamps, the output resistance of small signal output resistance of transistor is infinitely large. Okay, so let's neglect this R0 altogether. So this relationship will reduce to, I mean, we have to evaluate this for R0 equal to infinity. Okay, so everything else is known. We know what AV is. Okay, We know RS, we know RS. We know the input resistance, that's 200 kilos. The source resistance is given as 4 kilos. So everything is known apart from the transconductance gain. So from this information, the first thing you're going to do is find what is the transconductance gain. Okay, and this also appears as a resistance at the source terminal. Okay, so the choices is that you have a transistor threshold voltage given, this is negative for PMOS. Conduction parameters given as this is small kp prime, 40 microamps volt square. Lambda is 0. This transistor is available, and we are using this transistor in this configuration, source follower configuration. Okay, right. So all that we require now is to find this W by L ratio. Okay, so we have found RS. Okay, you can these are the same equations we used. You see, if you apply the Kirchhoff voltage law at the output loop over here, this is VDD minus the current IDQ RS is equal to, this will give you equal to VSDQ. Okay, so the voltage difference between the source and drain terminal. Basically, this is VS only because drain is set to 0. All right, so this is the equation. So you find RS as 4 kilo ohms from this auto KVL loop. Then the small signal transistor resistance, since lambda is 0, is infinity. So where is R naught? R naught is over here. Okay, so this is an open circuit. In this case, this is an open circuit. You don't need to bother about this. So your output voltage V naught is simply equal to, in this case, is GM VGS RS. Okay, VGS RS. And then, I mean, we have talked about this in the last lecture, so I'm not going to do this again. How do you write VGS is, you know that V in is equal to, if you apply KVL, Kirchhoff voltage loop in this direction at the gate source terminal, between gate source terminal and V in is equal, can be bifurcated into two voltage drops. So V in is VGS plus V naught. Okay, and you recall that V naught already contains VGS, so you bring this relationship over here. Okay, take VGS out, and then you can express your VGS and V in, okay, explicitly in terms of GM and RS. So we have done this before, actually. We had this relationship over here in the previous video lectures. Okay, and then you can do some mathematical artifice, and you can write this as 1 over GM. 1 over GM is this form is again voltage divider form. Okay, because you are adding ohms to ohms. All right, and you can find the overall voltage gain considering this equation. Just substitute VGS over here. Okay, and for V in, substitute V in, that will bring you VI, the original input voltage applied, that is going to drive the circuit. So this is your voltage gain. Okay, we are considering this voltage gain, and then this can be written as such. So we needed RS, but in this particular example, R naught is infinity. So we are not considering any R naught. All right. So you see R naught is vanishing in these expressions. The voltage gain is given as positive 0.9, 90%. So we know that R1, R2, the input resistance of the amplifier is, it depends on the biasing resistances, R1 and R2, which is given over here. This is my input resistance. So in this particular example, R1 and R2 is given as 200 kilos. Okay, so we have only this information for the input resistance, but we don't know what is R1 and R2 is. Okay, for now. So all right, so let's start plugging in the values. We calculated RS as 4 kilo ohms, so just plug these values in RS. Okay, the only unknown is 1 over GM. RI is 200 over here. Okay, so let's bring this over here. So we have these are the input resistances. So we are just plugging in the values in the voltage gain relationship, which is known as 0.9, and 4 is my output source resistance. Output source resistance is given as 4 kilo ohms. Okay, this is 4 kilo ohms in the connection. Then we find the transconductance gain, which is a little high for this transistor, which implies, if you remember, the transconductance gain is evaluated in terms of the Q parameters. Okay, in terms of Q parameters means you need IDQ, the quiescent drain current. Okay, this is the DC quantity. So the Q quantities are the DC quantities. That's where the transistor is biased. Okay, so this Q point, remember, this is in the center of the load line, and it's also in the active or the saturation region. Okay. So, so from this, since GM is now, you can find Kp as 0.784 milliamps per volts. Okay, and since transconductance parameter is given in terms of the electrical conduction parameter and the width to length channel ratios, so from here you can find your width to length channel ratio as 39.2. Now this is a large non-dimensional parameter. 39.2 is a large dimensional parameter. Uh, which means is that what it means is that for a large transconductance gain, you need a bigger transistor. Okay, I mean for by transconductance gain, I mean for a certain input, you need a large current. So the size of the channel should also be large. Okay, so that's what the physical significance is. So even you see over here, in order to achieve the desired specifications, a relatively large transconductance gain is required. What it means is that a relatively large transistor is needed. Okay, so you need a large transistor with a large channel to width ratio. All right, now if we do the DC analysis, if we complete the DC analysis in the design, then IDQ was given to us. If you recall, Kp we have found out that Kp, the conduction parameter, is 0.784. IDQ is 2.5. So let's find out VSGQ. VTP is known as -2. Okay, so that gives VSG as 3.79 volts. Now the quiescent source to gate voltage can also be written as, now this part is your is the voltage at the source terminal, at the source node. Okay, and this is the voltage at the gate. So the difference of these two is your precisely is VSG. Okay, I mean this is the DC analysis. So you can see in the circuit over here the gate drop at the gate voltage is given by this biasing resistances as R2 over R1 plus R2 into VDD. Okay, this produces your voltage at the, this gives you the gate voltage. Basically this is the gate voltage. What else? Well, we need the source voltage, source node voltage, and that is VDD minus IDQ, which is now into RS. Okay, into RS. This is equal to VS. This whole thing is equal to VS. So basically this is the difference of VS and G. Okay, so VSG is VDD minus IDQ RS minus this voltage divider relationship. So this is over here. Okay, this is VS, this is G, so this is VSG. Now we have everything. We know what is VDD, we know what is IDQ, we know RS. Okay, so by introducing a little bit of arithmetic, you can write this as 1 over R1, R2, R1 plus R2. Why we are writing this is because this is the parallel combination of R1 with R2, and therefore this is equal to the input resistance of the amplifier, Ri, which is given as 200 kilos. So we can plug this information over here. We can plug this information over here to find R1. Okay, so you see 200 is over here, so R1 is the only unknown. We know what VSGQ is, that's 3.79 volts. Okay, from the saturation voltage current relationship of the amplifier, since the transistor is operating as a linear amplifier. So okay, R1, R2 is my input resistance now of the amplifier, and then this is my VDD. Okay, so I have everything that is required to find R1. Now VDD is 20, IDQ is given as a quiescent current is 2.5, RS is 4 kilo ohms, so the only unknown that's left to find out is R1. So this gives R1 as 644 kilo ohms. And how do you find R2? Well, we know the parallel combination is 200 kilos. So let's use this one to find R2 as 290 ohms. Okay. Well, you also see that R1 R2 parallel combination is 200 kilos, so R2 was supposed to be less than 644 kilos. So the overall well, this is actually kilo ohms. Okay, this is kilo ohms. So the overall combination will produce the overall parallel combination is going to produce a resistance that is less than of these two resistances. These two resistances are 644 kilo ohms and 290 kilo ohms. So the parallel combination, you can see, is less than both of them, 200 kilos. Okay. Now a large value of input resistance, which is 200 kilo, has minimized the effect of loading due to the output resistance RSI of the signal source. Okay, so what it means is that uh, over here, if you look at the circuit, let me bring the small signal circuit over here. Yeah, so over here, what's going on is that V in, so I'm writing the node voltage V in terms of the voltage divider relationship. Well, V in can be written as Ri, which is a parallel combination of the biasing resistances R1, R2 divided by Ri plus RSI. So in this particular example, RSI is my 4 kilo ohms. Okay, multiplied by VI. This is the input signal over here. So I've just expressed the relationship between V in, the voltage drop at the biasing resistances, parallel combination of the biasing resistances in terms of the input signal voltage VI. So if Ri is much greater than RSI, in which case it's 200 kilos, RSI is only 4 kilos. So you can neglect RSI. I mean, your V in will be approximately equal to about 98% or 97%, something like that, of your VI. Okay. So in fact, all the voltage at the input, which is driving this amplifier, the source follower amplifier, is available at V in. Okay, at this node. Okay, so this is supplying the voltage to both VGS and the output voltage, right? So like this, as illustrated in this relationship. Okay, so you see there's a minimal loading effect. There's a minimal loading effect over here. If R1, R2 is large compared to RSI, you have all the input voltage available at V in. Okay, so there's a minimal loading effect. That's what it means. So a large value of the input resistance Ri has minimized the effect of loading due to the output resistance RSI of the signal source. Okay, that's all.